All right. So I want to go ahead and get started again because it's already past 10 o'clock. So a couple of announcements. So the final paper plan is going to be due next week. So I had one of you submit the final paper plan. Again, just to get you thinking about the final project, so you're not, offloading it until, the last week of the semester. So again, just submit a paper that you want to replicate. Tell me a little bit about the actual, data set you want to use, stuff like that, so I can get an idea what you want to do. So that's due next week. So tomorrow, you guys are all from Psych 505 anyway. So tomorrow we have a talk. There's going to be no workshop. It's just going to be the talk at noon. And the topic is going to be, it's a little complex. So it's going to be multi-level structural equation modeling. And the best way that I can describe structural equation modeling is like regression on steroids. And this is related to the question that Renata had before the break. So Renata listened to one of the podcast episodes from Quantitude. I think it was regression, that old friend from high school. And I believe the question was, what are some of the limitations of regression, or what kind of was the focus of that particular podcast? And one of the limitations that they talked about with regression is kind of like the workhorse for all of the statistical analyses that we're going to do. It pretty much underlies everything that we do, almost everything that we do. However, regression as a framework alone is very limited. It can't do a lot of things that we want to test, right? So the world that we live in is very complex. We have very complex hypotheses. We sometimes want to test mediation. We want to test moderation. We want to test moderated mediation. And regression alone, like we've been working with it, just can't do that. And in that particular podcast episode, they were talking about things like structural equation modeling, which can get at those complex hypotheses. So it was them kind of highlighting the importance of regression, but also talking about the limitations of regression and its inability to test really complex hypotheses that we're interested in testing. So when I talk about this, let's see if I can find like a figure. So psychologists, we like box and arrow plots. So with like structural equation modeling, we can test complex relationships like this, where we also have, these are latent variables, right? So these things are not observable. We've been talking about things that we can measure, but with structural equation modeling, we can, again, go really deep and we can test complex hypotheses about things that we can't even observe. So that, to answer your question, some of the limitations. Again, we're just talking about the basics of regression right now. And the next semester, we are going to talk about structural equation modeling, factor analysis, and some of these more complex things. But yes, so tomorrow's talk should be good. And Faustine, since you just walked in here, so next week, the final paper plan is due. So just submit a data set that you want to use and tell me a little bit about it, or a paper that you want to replicate or reproduce. That's all that I want, just to get you start thinking about it. Awesome. So to follow along, so all these slides are on the website, but what I'm going to try to do today is try to present it within RStudio, just so I can like write code, and then you also have the slides kind of on top of one another, so you can follow along. But if you want to follow along with the Cordo document, just go to that website and then download it, and you can follow along with what I'm doing today. So the plan for today is to talk about categorical predictors and how we can use linear model to make inferences about categorical predictors. Today I want to talk about 2 levels and then more than 2 levels. And then I want to talk about different coding schemes. So in order for us to use categorical variables in this linear model framework, we have to use coding schemes. We need to use weights. So I want to talk about the different coding schemes that are available to us, like dummy coding, sum coding, deviation coding. I want to talk about DIY, so do it yourself, or custom contrasts. Sometimes these are called planned contrasts. So how we can create those. I want to talk about the issues of multiple comparisons. And then I want to talk a little bit about plotting. So that's the agenda for today. So before we jump in, does anyone have any questions about what we covered before break? I know it seems like ages ago. Did everybody finish the lab on regression? Yes, submitted it. Awesome. No questions? So Wednesday is going to be a lab day. So if you have any questions about that, you can feel free to ask me during the lab session or just email me about it. I also posted the lab answers. So if you go to the lab page where it lists the link to get the actual lab, I have the lab answers for that. So you can find that here, right here. So I have the lab answers here, and hopefully it works. I'm using the WebR thing where you can go through and just click on each little code chunk. So hopefully that works. Awesome. So before break, we were talking about regression, and we were talking about overall model fit. And I talked about the F test and the F distribution, and I want to kind of revisit that before we proceed on, because we're going to be using this again and again and again. So in a linear model framework, we use sum of squares as our index of error, right? So we can partition the sum of squares. We can partition it into the explained sum of squares. So this is how well our model explains the data. And this is just the mean, the overall mean, minus the predicted values on that regression line. So this is the explained sum of squares error. There's also unexplained or residual sum of squares. And this is just the difference between the predicted points on the line and each individual data point. So this is kind of left over from the model. And then we have total sum of squares, which is the difference between this overall mean and each individual data point. And as we saw last week, we can add these up and then they should equal the total sum of squares. So if we add up the explained sum of squares plus the unexplained or residual sum of squares, that equals the total sum of squares. So what we can do is we can take these sums of squares and we can calculate what's called the F test. And the F test is just the sum of squares explained divided by what I'm calling degrees of freedom 1, which is just numerator degrees of freedom, which is p minus 1, and p is the number of parameters in your model. And what this equates to is the mean sum of squares explained error. And this is just the reduction in error achieved by the model. And we divide this by the sum of squares unexplained, divided by the degrees of freedom 2, which is the denominator degrees of freedom, which is just n minus p, which n is the sample size, minus p, the parameters. And this is the mean sum of squares unexplained error. And this is just how much variation is left from the complex model. And what we want is our mean sum of squares explained error to be larger than our mean sums of unexplained error. We want our model that we fit with our predictor to be better than just what's left over. And to do that, we compare our F test to a critical value from the F distribution. And this F distribution is the same as a standard normal distribution or a T distribution, right? So it's kind of this null distribution. And ideally what we want is our F value to exceed this critical value. And if it does exceed this critical value, then P is less than 0.05. We can say that our predictor model is better than a model with no predictors. And that's essentially or ideally what we want when we're doing this test. If it's not significant, then our predictor that we built up or the model that we built up with our predictors doesn't really explain much, which is something that we don't want. So does that make sense to everyone? I know there was some confusion before break when I was talking about this, but hopefully this makes a little bit more sense now. So today we're going to be looking at categorical variables, and to model categorical variables, I want to use a data set from Bodo Winter. And in this data set, he has various words, so things such as acidic or acrid, and these represent various modalities or senses. And for the first part, at least, I want to look just at two senses. So we're going to look at taste and smell. So let's go ahead and load in our data set. Here, I think I have it all. Then we can look at the actual data set itself. It's taking so long. There we go. So if we actually look at the data set, there's 3 columns in our data set. There's a word column, there's a modality column. Again, we're only looking at 2 senses, taste and smell. and then there's a valence column. And what individuals did is they rated these words on a scale from 1 to 9, with 9 being more pleasant and 1 being unpleasant. And what question we want to answer is, are smell words like rancid rated as more unpleasant than taste words like sweet? So that's our question for at least the first part of class. So far we've been fitting a linear model where our x sub I is continuous. But we can actually extend this and we can replace this x sub I with some type of categorical predictor. And that's what we're going to be doing today. But before we proceed on, there's some terminology that we need to know. So when we talk about categorical variables, we talk about factors. So this is just a variable with a fixed set of categories. And then we also talk about levels within that factor. And these are the individual categories within a factor. So in our data set, what is the factor and what are its levels? And this is a question to you guys. So if we're working on our data set, we have word, we have modality, and then we have valence. What is our factor here? Yeah, so modality is the factor, and then within modality, we're working at 2 senses, right? So taste and smell. So that means that there's 2 levels associated with that particular factor. And I make a note here that when we're working with categorical variables and we're trying to perform regression on these categorical variables, we need to make sure that the factors are set to be factors within our data set. That's very, very important because it can have some downstream effects that we don't want. So to check that our factor is in fact a factor, what we can do is we can use this is factor function, not if factor, is factor. Let's see if I can get its senses. So we can run is factor, and that will tell us if it's a factor, and it says it's false, so it's not a factor. So how do we turn it into a factor? So there's a couple ways that we can do this. And all this code that I'm writing, I'm going to regenerate it, and then I'm going to post it on the website too. So we can use the mutate function, and we can say modality is equal to a factor. And this will turn our factor into to make sure that's an actual factor. Another way that we could do this is we could do modality is equal to as factor. And this will make sure that our factor is in fact a factor. Run that. So when we are fitting a linear model, what we're doing is we're trying to fit this line, and we're trying to fit the best fit line. And the best fit line is one that reduces the sum of squares error mathematically. When we're talking about categorical predictors, we're interested in the mean differences between conditions. So here what I have is a visualization of our 2 modalities, smell and taste. And we have valence on the y-axis, and then we also have their means, which you can't really see here because this projector sucks. So hold on. Let's see here if these can be better. So that's a little bit better. So we have the mean for each group. And we're still fitting a line, right? So we're going to fit this best fit line, and this best fit line is going to go through the mean for each of these groups. But we have a problem. So we have 2 equations now. So we have an equation for the intercept of mean, or of the mean of smell. And we also have another equation for the mean of touch. So the question becomes, how can we just get one linear equation to use our general linear model framework? And the answer to that is mathematical wizardry. No, so it's not wizardry. Essentially what we're doing is we are applying numeric codes or numeric weights to our categorical levels. And this allows us to derive means, so means of each of those groups, but also allows us to derive contrasts or differences between those groups. And we can use that to make inferences that we're interested in. And one of the most popular coding schemes is dummy coding or treatment coding. Is this something that all of you guys have been exposed to or heard of? Awesome. Well, in R, anytime you feed it in a categorical variable, it will default to dummy coding or treatment coding. So you can just throw in a categorical variable, and this is what type of coding it'll apply to. But just to get the basics of it, you start with k levels. In our case, we have 2 levels. And what we're going to do is we're going to break it into k minus 1 dummy variables. In our case, we only have 2 levels. So k minus 1 is 1. So we're only going to be creating 1 dummy variable in our data set. And this just involves assigning something to 0 and the other thing to 1. And the thing that's coded as 0 is going to be our baseline or reference level. R does this automatically, just based alphabetically. So whatever comes first in the alphabet gets labeled as 0, and the other thing gets labeled as 1. In our data set, smell comes before taste. So smell is labeled as 0, and then taste is labeled as 1. So we can take our linear model equation that we have up there, and what we could do is we could place this x sub I with our indicator variables. So for smell, x equals 0, we can just input that into our equation. And essentially what we get is just the mean of smell. So the mean of smell is equal to the intercept, b sub 0. To get the mean for taste, what we can do is replace this x sub I with 1. And the mean of taste is just equal to the intercept, b sub 0 plus b sub 1. And that gives us the mean of taste. So let's go ahead and actually just dummy code this into our data set itself. And to do that is fairly simple. We're going to use a mutate statement or a mutate function, and we are going to create a variable that's our dummy coded variable. So what I have here is I'm just fitting the model, so census filt, and then I am calling a variable mod, and I'm using an if else statement. So if modality is equal to smell, I'm going to assign that a 0, and if it's not, I'm going to assign it a 1. So we can go ahead and look at what this looks like. This, sorry. Sometimes the visual editor doesn't want to work. I was going to call it on the console because it's being difficult. But yeah, so if we call that data set, we can see that the variable that we created, mod, now has 1s or 0s for our character variable or a factor, right? So 1 is taste and then 0 is smell. So now what we can do is we can take that variable and we can input it into our linear model and run a linear regression on it. So what I did here is just call the linear model, and I'm assigning that to LM treat. And then what we have here is just the summary estimates or summary output. So let's run this into the console. Maybe it'll work this time. Let's see if this will run. Let's see if we can make this bigger. So if we run that linear model, we're going to get these estimates. So we have our term, our intercept term, which is 5.47, and then we have our slope term, which we labeled as mod, and then we get an estimate for that. So let's go through each of these estimates and kind of explain what each one, or how we interpret each one. So in this case, what does b sub 0 represent? So 5.47, how can we interpret that particular estimate? So what does 5.47 in this context represent? So remember when we were working with just a regular regression with a continuous variable, similar interpretation. So do you remember what that interpretation was?
In this case, it's the mean of whichever one is 0. I can't remember which one.
Yeah, so whatever comes first alphabetically. So we didn't set that specifically. So yeah, it would be just the mean of smell. So as Kennedy said, the mean of smell, which is 5.47. We can also say when x equals 0, smell in this case, y is equal to 5.47. So essentially what this represents is just the mean of our smell variable. So now we have this slope estimate here of 0.337. What does that represent? So here, let's look at a visualization that I think is fairly helpful. So as we just said, the intercept is when x equals 0. So it's the mean of y when x equals 0, which is our Snell group, right? So what the slope represents, or our beta 1 estimate represents, is the difference between those two conditions divided by run. So do you remember how we interpreted a slope for a continuous predictor? So in a continuous context, when we have a slope, how do we interpret that particular estimate?
Is the increase of y when x increases 1?
Yep. So a 1 unit increase in x leads to an increase or decrease in y. Here, this 1 unit increase is just going from one category to the other. So it's going from 0 to 1, which is a run of 1. So the difference divided by 1 is just the difference. So here our slope represents the difference between those two conditions. So let's go back to our interpretation. So the estimate itself is 0.337. So how do we interpret that? So let's write an interpretation of that. Back to that. So we can say that it's the mean difference between the two groups, right? Or we can say that if we go from one category to the other, there's a 0.337 difference. So that's how we would interpret our slope parameter in this context. And what we can do with our estimates here, 5.47 and 0.337, is that we can derive the means mathematically or by hand. And to do that, we could just write our equation. So 5.47, which is our mean for smell, plus 0.337, and then we can multiply that by our dummy codes. So if we multiply this by 0, and then if we do the same thing for 1, this probably won't run. That's not right. So we get 5.47 if we times 0.337 by 0. So that's our mean for smell. And then we can times 0.337 by 1, which is our dummy code for taste. And that gives us the mean for taste. So that's how we can derive these means from these dummy codes. So far we've been working with a reference level that just comes first alphabetically. We're just letting R dictate to us what the reference level is, but that doesn't have to be the case. We can choose what our reference level is. And here what I've done is I've used the function relevel, and I've just switched the reference level to taste. So that's one way you could do it. The other way you could do it is just using a mutate if else statement, where we can assign this explicitly. So if we go back up to some of the code that we wrote. So if we look at the code that we wrote, right, so we could just, say that modality, if it equals to smell, we can just say that it's 1, and then it'll give the other one a 0. So that's how we could do that by hand or explicitly, or we can just use the re-level function here, which will do that for us. If we rerun the regression analysis, we see that the intercept now is 5.80, which is the mean for taste. It's not the mean of smell. Also, the estimate, the difference is still 0.337, but obviously there's a sign flip because we're doing subtraction a little differently here. So it's the same difference, just have a different reference level. So treatment coding, dummy coding is probably one of the most popular coding schemes. Another popular coding scheme is contrast coding or sum to zero coding. And this is what I primarily use a lot in my work. So when we're using treatment or dummy coding, 0 is our reference level or our baseline level. When we're using sum to zero coding or deviation coding or sum coding, what we're doing is we're changing the intercept now so that the x point, or when x equals 0, is the grand mean or the mean of the means. And these two things are equivalent when we have equal sample sizes in each of our groups, right? So we could take the mean of one group and then the mean of the other group and divide by how many groups that we have. And that's essentially our grand mean or the mean of means. When we don't have equal sample sizes, then this particular equation or this particular formula doesn't work. But we can add weights to each of these means. So we can times these by the number of participants in our sample sizes to get the grand mean if we want to. But essentially, with treatment dummy coding, the x equals 0 is related to a particular group. Here, the 0 point is just the mean of the means or the grand mean. So that's one of the main differences between these two types of coding schemes. So there is lots of confusion over these terms. So what I'm going to be talking about today might not be something that you read. They might call it something else. But just for simplicity, I'm going to follow Lisa de Bruin's definitions. If you go to that website, she has kind of some of the definitions for all these different coding schemes. So I'm going to tend to follow that. When I talk about 0.5 or negative 0.5 coding, I'm talking about deviation coding. And as we talked about, the intercept is the grand mean now when we're using deviation coding. And the slope is still the difference. So let's go ahead and manually code this into our data set. So instead of using 0, 1, what we're going to do is we're going to use positive 0.5 and negative 0.5. And this is going to be our deviation codes. And similarly to the treatment coding, we can use if-else statements. So we can say that if it's smell, we're going to give that a 0.5. And if it's not smell, we're going to give it a negative 0.5. So that's one way that we could do this, like coding it manually into our data set. There's also a function called contrast that will allow us to assign contrast to our levels. So here what we're doing is just using the contrast function, and then we're just saying that the first level of that factor is 0.5, and then the second level is negative 0.5. So that's an additional way that we can do that. And as I show here, if we call that particular variable, we can see that now smell is 0.5 and taste is negative 0.5. So let's go ahead and take our variable that we created, our deviation coded variable, and put that into our linear model. So if we run our linear model here, we get our estimates, right? So we have our intercept estimate, and then we also have our slope estimate. So here, what does B sub 0 represent? So here it's 5.639. What does that represent in this context with deviation coding, 0.5, negative 0.5 coding?
mean of the means of taste and smell?
Yep. So it's the grand mean, and we can actually work this out if we want to, just to prove it. So we can take our data set, so census filt. We can group by modality. We can grab the mean. So we're going to get the mean of valence. We're going to ungroup, and then we're going to summarize again, and this is going to give us the grand mean. So if I did everything right, it should be yeah. So 5.64, that represents our intercept here, 5.64. So again, this is just showing you that the intercept in this context is the grand mean, or the mean of the means. So write that down here. So let's move on to the slope estimate. So the slope estimate here is 0.337. So what does that represent? You have to remember from a couple of slides ago, but what 0.337 represents is just the difference between those two groups. Smell and taste. So that's what the slope represents when we're talking about deviation coding. And we can take this information from our estimates or from our summary output, and we can basically by hand calculate the mean of smell and the mean of taste. And we could just take 5.64 times that by our difference, multiply that by our deviation code, so 0.05. So 5.47, and then 5.8. So those are our means for taste and smell. So again, hopefully building up an intuition of how we can take all of this information and extract things that we want, like the means and also mean differences. Another popular type of coding scheme is sum coding. And when I talk about 1 or -1 codes, I'm talking about sum coding. Again, people use different terminology for these things. So I try to be as consistent as possible. But here, instead of using 0.5 and -0.5, we're just using 1 and -1. And similarly to what we were doing before, we can just create an additional variable in our data set. And we can say that if it's equal to taste, or should be smell, we're going to give that a 1. And if it's not equal to smell, we're going to give it a -1. We can also use the contrast functions that we went over. And let's just do where we assign it 1 or -1 to our variable. And that will give us 1, -1 contrast codes. So when we use -1 and +1 codes, the grand mean is still the intercept when x equals 0, right? So these still sum to 0. What's different is the slope interpretation. So now when we step from one category to the other, or one mean to the other mean, it's not a run of 1, it's a run of 2. So the estimates that are produced by the model are halved. So we can look at a visual interpretation of this. So we have our grand mean here in the center, and then we have our group that we coded as -1, and we have our group that we coded as 1. So hopefully we can see that to go from -1 to 1 results in a run of 2. So our estimate is halved. And we can fit a model and we can show that here. So we can take our -1 + 1 variable that we coded, and we can run a linear model on that. And these are our estimates here. Yeah, Alex.
Why would someone want to do that?
Good question. So I agree with you. I prefer to use positive 0.5 and negative 0.5. Sometimes people don't really think these things through, and they don't know the defaults. But sometimes people are not really interested in the estimates themselves. So the choice of coding that we use doesn't change our statistic or our p-value. But I'm with you. I don't know why anyone would use -1 or +1 coding. It could just be a preference. It also is because this type of coding is default in R, and I don't know if it's default in Python. But if you do like a sum coding contrast function in R, it'll default to -1, +1. But again, what I want to highlight here is that regardless of the codes that you use, the statistics and the p-values are essentially the same. But yeah, no, I agree with you. I don't know why someone would want to use the +1, -1 coding schemes, but people do. So we can fit this model with this -1, +1 coding scheme. And we have our intercept here. The intercept is still the grand mean, right? 5.64, which is what we calculated. All right, so the grand mean. Smell and taste. And then we have our slope estimate here. And we can see that the slope estimate is halved, right? So if we remember, the actual difference between those two groups was 0.337. Now it's 0.168. So the interpretation of this estimate is a little different. So how we interpret the slope estimate with this type of coding is that it's basically the difference between what we coded as 1 and the grand mean, which is half the difference between the two conditions. So that's how we would interpret that particular estimate within the context of this +1, -1 coding scheme. So to go back to Alex's question, why would we ever use 1, -1? In my work, I don't like using 1, -1, but that's because I like to interpret the estimates, themselves. And with the -0.5 and +0.5 coding scheme, we can interpret the estimate as the exact difference, which I would report in my paper. When we use -1, -1, +1, it's half that difference, right? So that's why it's important when we are doing these type of things with our variables that we be as transparent as possible when writing this stuff up. So I can't tell you the countless times where people will write result sections in their papers and they won't say what type of coding they used. So you're just left to guess. But hopefully now you can see that the interpretation of these estimates could be drastically different depending on the type of coding scheme we use. So if I were to use some coding here but not say it, then this is not the actual difference between those two conditions, right? It's half the difference. But that's why I like to use deviation coding, because again, it codes the actual difference between those two conditions. But you just want to be transparent and report what type of coding scheme you used. And then obviously talk about the difference between the two conditions, and then also provide p-values and all that good stuff. So what I wanted to talk a little bit about here is that what we just ran is basically the same thing we would get if we ran a t-test. So what I've done here is just run a t-test with the base R function. And this is the output from that t-test. And you'll see that we get the exact same results without the coding. So we see our estimate is the difference. We have the two means per group. And then we have our test statistic, our p-value, and our confidence intervals. These are the exact same as what we computed here with our dummy coded variables. Just to give you a sense of how these two things are related. So are there any questions about contrast coding or treatment coding in the context of two levels? Questions, concerns? Yeah, Alex.
how, it's been a while, but
Yeah.
is there not another one where you like squeeze the values between like a probit or like a function where the interpretation it's like a graded thing as opposed to categorical?
Are you talking about like a like polynomial type of thing, or
No, like when the interpretation of like between 0 and 1 is like a probability.
yeah? So those are more like transformations. Are you talking about like the logistic transform,
Yeah.
where we're just like going back between like the log odds to probabilities?
Yeah, did we go over that earlier, or is that?
No, we did not go over that now. So in this context, that's a little different. That would be like if we're fitting like a logistic model or like an ordinal regression model. So different things. But even in that context, we could use dummy coding or contrast coding to look at the differences in probabilities between the two conditions, let's say. All right. So we talked about 2 levels now. Now I want to extend it to 5 levels. So if we go back to our data set that we originally started with, the census data set, we winnowed it down to 2 levels, but there's actually 5 levels in that data set. So let's go ahead and work with 5 levels. So if we were just going to fit a linear model from our census data, so we enter in modality as our IV and valence as our DV and just run that linear model, we're going to get something that looks like this, where we have our intercept value, and then we also have 4 estimates or 4 slope estimates: modality smell, modality sound, modality taste, and modality touch. So what's going on here? We have 5 levels, but there's only 4 estimates here. So if we remember what I was talking about in terms of dummy coding or just coding in general, we have to fit k-1 codes. We don't need to fit all 5. So we can extend our dummy coding that we did with 2 levels to 5 levels. And here what we're going to do is we're going to assign a baseline level to one of our values or one of our levels. So here it would be smell. And then we're going to have 1 dummy code where we're going to assign 1 to the first group and then 0 for the rest. We're going to do that for the second dummy code. We're going to do that for the third dummy code. It's quite common to look at these things as in a matrix. So here what we have is we have rows of our matrix, which are each of our levels. So sight, smell, sound, taste, and touch. And then for columns, we have each of our contrasts, or our k-1 contrasts. And for the smell sight contrast, we see here that our reference here is sight. This is labeled as all 0, so that's going to be our reference level. But for this first contrast, we're assigning 0 to sight and then 1 to smell, and then everything else gets a 0. For the second level, we're comparing sound to sight, and we're going to give 0 to sight and then 1 to sound. We're going to do the same thing for taste, and then we're going to do the same thing for touch. So that's how we're going to construct this dummy coding for multiple levels. So this is kind of a visualization of what's going on here, right? So each of those slope estimates that we're calculating is just the difference between a level and the reference group, right? So x sub 1, or our first slope estimate, is just the difference between the first level and the reference. The same thing for the second estimate, the same thing for the third estimate, and the same thing for the fourth estimate. So it's each level compared to a baseline level. So we can do this by hand. This would involve us calculating lots of columns in our data set and then feeding those into our linear model, and no one has time for that. There's some really useful functions in R that will do this coding for us under the hood. One particular function that I like is from the faux package. There's one function called the contra code treatment that we can just feed in our vector into, and it will do this dummy coding for us. So let's see, let's run that here. Good spell. So we can just feed in that particular factor into this function, and it's going to do all the contrast stuff that we just went over under the hood. There's also another function called contra.sum, which is kind of a base R. And I don't like that. That's what it's doing under the hood when we're just feeding in that variable into our linear model here. All right, here. And there's one reason why I don't like this is because it's not really intuitive what the actual estimates represent. It just says modality smell. With the contra sum or the contra treatment function, we actually get more intuitive estimates where it's like smell versus sight, sound versus sight, taste versus sight. So it's a little bit more intuitive. That's why I like that compared to the base R one. But again, we get the same estimates that we would get when we're just fitting a regular linear model and just throwing that modality factor in there. So we can also apply sum coding to our variables. So we don't have to do dummy coding, we could do sum coding. And if you remember, sum coding is this 1, -1 coding scheme. And within sum coding, the intercept is still the grand mean, but the estimates that we see are each level versus the grand mean. And to do this, what we do is we assign 1 to our target level, we assign -1 to a non-target level, and then 0 to things that are not involved in that contrast. So here is a matrix form of what I was just talking about, right? Where we have our levels as rows, and then we have each of our contrasts as columns. So we can see here that the intercept is the grand mean, but we're assigning 1 to what we're going to compare that intercept to. -1 here is the variable that's just dropped from analysis. So you will not see this contrast in the report or in the estimate summary. You would have to re-level or redefine what your non-target level is. And when we're doing sum coding, it's usually just the last level of the variable. So one thing I didn't go over is that you can actually just look at the levels. And it's going to be important when we're talking about applying contrast. So each factor has particular levels. There's the first one, second one, third one, and fourth one. So we need to make sure what our levels are because that's what's going to be dropped or that's what's going to be our baseline or reference category. I think that's... So modality is not a factor. So let's see if we can just do... Nope. Let's just do... So yeah, so we can use this levels function here, and this will tell us the levels of our factor. When we're doing sum coding with multiple levels, the last level is usually just dropped. But we can change that. We can put it back in if that's a particular contrast that we care about. But that's just what R is doing underneath the hood. So we can rerun our analysis using the contrast code sum function. This will do this sum coding under the hood for us. And we can see that now we have our intercept, which is the grand mean. And then we have our estimates here, which are a particular level compared to that intercept level. So again, more intuitive estimates here. So sight minus intercept, smell minus intercept, sound minus intercept. So to go back to Alex's question about why someone would do something like this, so you might have questions about a particular level compared to the grand mean. I know in my work, I don't have those questions, but one of you might have those questions. On Wednesday in lab, there's a particular question that would require some coding. But again, you might be interested in a particular level compared to the grand mean, and then you can use this sum coding stuff. But honestly, people just kind of throw things into the linear model function and just run it, and there's not really any thought into it. But you might have some specific questions about a particular level compared to the grand mean. Then you'd use this type of sum coding. So my personal favorite is deviation coding, as I just said. In deviation coding, the intercept is still the grand mean. And our estimates are actually the difference between a level and a reference level that you define. And here we have to use the coding a little differently. So our target level gets k-1 divided by k code, and non-target levels get -1 divided by k. And that's what we would assign to our variables. And the one that is assigned the k-1 divided by k is the target level, and that's compared to a reference level. So we can do this manually, and I just kind of wanted to show you how this would look manually, but we could create separate, or we could create 4 contrast codes where we're using if else. And what we're saying is modality, if that's equal to smell, we're going to assign that 4/5. And then all the other levels get -1/5. And then we could do that for sound versus sight, taste versus sight, and touch versus sight. And again, sight is just the baseline level. You can put whatever reference level you want, depending on what difference you care about. But this is kind of how you would do that. And this is what the actual contrast matrix would look like, where for smell versus sight, right? So smell gets a 0.8, and then everything else gets a -0.2, and that's compared to sight. Same thing for sound minus sight, 0.8 for the sound level. Everything else just gets a -0.2, and then the same thing for taste sight, and then touch sight as well. So we don't have to do this by hand. There's a function from the faux package. This one is called contra code ANOVA. So again, this goes back to the issue where things are called something different by each individual person. So sometimes this is called ANOVA coding, but we're just going to call it a deviation coding. But in that particular package, they have a contra code ANOVA function that will do this deviation coding for us. So we can fit that new variable into our linear model, which is deviation coded, and then we get our estimates. So we have our intercept, which represents the grand mean. Then we have each estimate that represents a particular level compared to a baseline level. Here, smell sight, sound sight, taste sight, touch sight. And if you have time later, going back to this stuff, you can look at the means. So you can calculate those means, and then you can actually, subtract them to make sure that this matches up with what you coded, which I recommend that you do anyways. So this should represent the exact difference between those two conditions. So now you might ask, Jason, what if I don't care about pairwise contrast? What if I don't care about like smell versus taste, or touch versus sound? Like I don't really care about that. Well, you can create your own contrasts. So I call these DIY, do-it-yourself contrasts. Sometimes this is called plan contrast. So at the onset of your study, you might have specific hypotheses that you want to test. So what I want to do is go over the rules to creating those contrast codes so you can get those actual differences in your data set. And you can have an estimate, and you can have a t-test associated with that and a p-value associated with that. So when we're creating our own contrast, the general rule of thumb is that you only look at 2 chunks of variation. So what do I mean by 2 chunks? This can mean that the contrast compares one level to another level, right? It can mean that you compare 3 levels to 1 level. You can compare 2 levels to 2 levels, but ideally what we want is just 2 chunks. And these chunks can have different groups in them, but just generally should have 2 chunks. And rule number 1 is that you assign one of those chunks to be positive, and you assign the other chunk to be negative. It's arbitrary. You can flip those around if you want. Rule 2 is that the sum of the weights that you use should be 0. We want to test orthogonal contrast. Rule 3 is that if a group is not involved in your contrast, assign it a 0. Rule 4 is that you should have some initial weights that equals the number of groups in the opposite chunk. And then rule 5 is to get the final weights, you just divide that by the number of non-zero weights. So what does this look like in practice? Let's go back to our modality data set. And let's say that we're not interested in, smell versus sight or touch versus taste. Instead, we're interested in chemical versus non-chemical senses. So we have 2 chunks here where we want to compare smell and taste to sight, touch, and sound. So again, in our first chunk, we have 2 groups. In the second chunk, we have 3 groups. So the first rule is that we assign a weight, right? So we decide which one we want to be positive and which one we want to be negative. It's arbitrary. So here we're just going to assign positive weights to smell and taste and then negative weights to sight, touch, and sound. The magnitude equals the number of groups in the opposite comparison or the opposite chunk. So here we're saying that it's 3 because there's 3 groups in the opposite chunk. Here we're saying it's 2 because there's only 2 groups in the opposite chunk. Then we assign initial weights, which is basically just the magnitude for each of the levels. So we have 2 3s here and then 3 2s here. And then the final weight is just this magnitude or initial weight divided by the number of non-zero contrasts. So here, there's no zeros. We're using all 5 levels. So basically our 2 weights for the smell and taste condition are 3/5 and 3/5. And for sight, touch, and sound, it's -2/5. And this final weight is what we're gonna input into our analysis. And to do that, what we have to do is basically create an array of weights. So what I'm doing here is I have an object, taste, smell versus all the others, or chemical versus non-chemical. And basically I'm assigning the weights that I just created. And this is related to the levels that we just looked at. So again, this is why levels or looking at the levels are important, right? So we have levels of sight, smell, sound, taste, and touch. We need to make sure that we're entering in our weights properly. So we have to look at our levels here. That's why I have assigned -2/5 and then 3/5, -2/5, 3/5, and -2/5. So that's our contrast for this comparison. What we have to do then is we have to create kind of a matrix like I showed you. And to do that, we can do this cbind, or we can use this cbind function. So you get something that looks like a matrix. So you can have multiple comparisons if you want them. But here we just have our rows, which represent our 5 levels. And then we have our contrast code here with the proper coding scheme. We have to make sure that our variable is a factor. I just assigned that as a factor here. And then we can apply that contrast code to our factor by just using the contrast function. And we can run our linear model with this. And the estimate that we get should be the difference between the chemical and the non-chemical senses. Let's see here. Yeah. So we see that the first estimate is our modality, taste, smell versus others, and that represents the difference. And you'll notice that there's also other estimates here. So R will just create other contrasts for you because again, it's creating the K-1 contrast. But if we only care about that one value, then we can just use that one value and denote if it's significant or not. So does that make sense? Yeah.
What's the motivation to do this compared to just dummy coding, like chemical versus non-chemical?
So you wouldn't be able to do that within the dummy coding. I guess you could do like assign 0. So you wouldn't be able to do that because you need to assign a reference level, right? It's like you wouldn't be able to code this particular contrast in a treatment coding scheme. Because I'm trying to think, so it's assigning 0s and 1s, right? But the first one is a contrast. So like, I guess you could assign 0s. No, it wouldn't work. So it's going to assign the first level as a reference category, right? So you could do like post hoc, maybe like combine them where like you will combine them manually, but you don't want to do that because then you're messing with the actual factor itself. But yeah, it would be hard to do that within a dummy coding framework. All right, so we've been working with 3 or more levels. And we've been using this general linear model framework. Well, we can just use the regular F-test to look at this, right? So this is basically an ANOVA, an analysis of variance. And when we're using the F-test, we are interested in comparing the null hypothesis, which there's no difference between the groups, to an alternative hypothesis where there are differences between those groups, as denoted here. And again, we have to say hello to our sums of squares again. And again, this projector is horrible, but I like this visualization from Andy Field because I think it does a nice job of partitioning the sum of squares in like an ANOVA type of model. but we have our sums of squares total, which is the difference between the grand mean or the overall mean and each individual data point. We have our sums of squares residual, which is each individual data point minus the mean for that group. And then we have our sums of squares model, which is the difference between the overall mean and the mean for each individual group here. And similarly to what we did before, right, we can kind of partition this and we compare an empty model where there's only one mean, right? And that error is the sum of squares total, to a full model where each individual person has their own individual mean, right? So they're in each individual group, and we're basically just taking the individual observation minus that individual's group mean. And that error is sums of squares unexplained. So we can take all of this and do what we've been doing before, right? So we have our degrees of freedom here. We also have our sums of squares total and sums of squares unexplained. Kind of went over that at the beginning of class. And then we can use this information to calculate our F-test, which is the mean of squares explained divided by the mean squares unexplained. And we want to compare this F-test to a critical F value, and we want to see if it's less than 0.05. If it's less than 0.05, then we can say that our model with our predictor explains some of the variance compared to a model that has just one mean here. So we're saying here that our model and our predictor model does a better job than a model with just one mean and no mean differences. So we can calculate an ANOVA based on this. Just to kind of just show you, we can create two ANOVAs where we can create an null ANOVA, which just has valence, so one mean, and we can compare that to an ANOVA that has our modality factor here, and then we can run an ANOVA on that. So this ANOVA function is just going to compare these two ANOVAs together. And it'll give us an F-test and also give us sum of squares and residual sum of squares, everything that's the same as if you were just to do a regular ANOVA model. So again, just to highlight that it's doing this comparison between an empty model with one mean to a full model with multiple means here. So we can just do a regular ANOVA. Or super ANOVA if you want to use what the book uses. But yes. So we can feed that in and we get our F value, and then we also get a P value associated with it. So if we were using the ANOVA framework, we would say that the factor of modality is significant, but we're not doing any dummy coding or contrast coding here. Instead, what's commonly done are what's called post hoc comparisons, where you extract the means and you do these pairwise comparisons. So now I want to introduce one of my favorite packages called M-means. It's my second favorite package next to the EasyStats ecosystem. But yeah, no, I love M-means because it makes it so easy to do these comparisons. So with M-means here, you feed it in the model. And what I like about this is that it doesn't have to be an ANOVA model. You can feed it in a linear model too. Like if you're like, I don't want to do any of this dummy coding stuff, I don't want to do contrast coding, just use M-means. And this is what everybody uses anyways, to get the means for the model and then also to do the comparisons for the model. But here we're going to enter in our model, and then we're going to specify a factor with the specs argument, and it's going to output the means for each of our conditions here, along with other good stuff that we want, like the standard error and the confidence intervals. We can then use the pairs function that I have highlighted here. Ignore the knitter cable function, it's just pairs and then the means that we calculated. And this will give us all of the pairwise comparisons between our levels. And it will give us the difference, and it will give us the associated T value and the P value for that difference, which is essentially what we want. It makes it super easy to do that stuff. And if we had our planned comparisons, right, we didn't care about all the pairwise comparisons, we can even input in our particular contrast that we're interested in, which is the chemical versus non-chemical. We can use this contrast function and then input in our matrix. And basically we can get an estimate for that difference here. So we don't have to even worry about the whole linear model framework. We could just enter all this stuff in here and then have the program calculate it for us. But yeah, this gives us our contrast, our estimate, which is the difference, and then the t-value, p-value. So it tests our difference for us. So I've been talking about all these pairwise comparisons. So we have to go back to alpha, which is our type 1 error rate, and we want to keep that at 0.05, right? We want to give us only a 5% chance that we're going to make an erroneous conclusion. That's for one test. But here we're calculating multiple tests. So what happens is that it increases what's called our family-wise error rate. And the family-wise error rate is 1 minus alpha to the power of k. K is the number of comparisons that we're doing here. So if we were to do 10 comparisons, our alpha level wouldn't be at 0.05 anymore, it would be like 0.40. So that's called alpha inflation. So when you're doing lots of tests, it's going to inflate our alpha. So we need a way to control our alpha and keep it at 0.05. And there's a couple different procedures that we can use to ensure this. One of the most popular ones is the Bonferroni correction, and I think it's one of the easiest to apply. It's simply taking the alpha level and divide it by the number of comparisons you want to use. So if we just have 3 p-values or 3 comparisons, essentially we just take our alpha level and divide it by 3, right? I don't know what that is. So it's 0.016. So each p-value that we calculate, we compare to that new alpha level, that adjusted alpha level of 0.016. If it's less than that, then we can say that there's a significant effect. If it's greater than that, then we say that there is no effect. So this is used quite frequently. It's very easy to apply, but it can be conservative in that it leads to lots of false negatives. So we have to be concerned about that as well. When we're using the Bonferroni, we usually report adjusted p-values, and this is just the p-value that was originally calculated multiplied by the number of tests that we want to use. And luckily R has a function that will do that for us. There's a p-adjust function. You can tell it what method you want and then give it the p-values, and then it will give you corrected p-values that you can report in your paper. So as I said, the Bonferroni leads to increased type 2 error. A procedure that balances the type 1, type 2 errors a little bit better is the home Bonferroni correction procedure. And this one is a little different. So in this particular context, what we do is we take our p-values and we sort them from smallest to largest, and we assign a rank to them. So the first one would have a rank of 1, the second one a rank of 2, the third one a rank of 3. And what we're doing is we're testing these p-values against an adjusted p-value. And the adjusted p-value is alpha divided by m plus 1, m is the number of comparisons, minus k, which is our rank. So what we do is we go through each one of these and we compare this p-value to this adjusted p-value. If our p-value is less than this adjusted p-value, then we can say it's significant and we reject the null hypothesis. Then we move to the next one and we test it again. But we have to make sure that we are calculating the correct rank. So if we test the second one, k is equal to 2 now, not 1. And then if that's less than, so if this p-value is less than this adjusted p-value, we can reject the null. If it's greater than, then we can't reject the null hypothesis. And each subsequent p-value that we're going to calculate we're not going to be able to reject that null. So we would just stop the procedure and not go forward with it. When we're reporting the home Bonferroni p-values, what we want to do is we want to take our p-values and then just multiply them by the adjusted denominator, this m plus 1 minus k. And that's what we would report in our paper. And p-adjust and R will do that for us. And as you can see here, we have our adjusted p-values here. There are lots of multiple comparison corrections out there. There's the Tukey, Chaffee, the Dunnett. Find out what your field does and just use that. For me personally, I tend to use like the home Bonferroni or the Bonferroni correction just because it's so easy to use, but your field might do something different. And all of these comparison corrections are in m-means, so we can use those. Whatever you want to use, you can use, right? So we talked about this pairs function where it gives you the pairwise comparisons. Well, there's an argument called adjust, and you can put in your adjustment here. So here I'm just using Bonferroni, but you can use Dunnett, you can use Tukey, and it's going to give you those corrected p-values. So these are Bonferroni corrected p-values. This is what you would report in the paper. If you wanted to use the home Bonferroni, you would just change the adjust argument. One thing that people don't do that we should do, and I'm guilty of this, is to include your confidence intervals adjusted for those multiple comparisons. I know no one that does this, but we should be doing it. And it's fairly simple to do, especially in R, where we can run our pairs procedure, and then we can just calculate our confidence intervals around those pairs. And this will give you the adjusted confidence intervals that's adjusted for the comparison procedure that you're using here. And again, people do not do this, but we should be doing this for our differences. What I have here is just kind of if we're going to write up in ANOVA, what we should include in it, right? So we should talk about our factor and if it's significant or not. But we should definitely also include our post hoc comparisons. So each difference that's significant or not significant. We should also include our alpha adjustment used. And then also the adjusted p-value. So when I say alpha adjustment, say that you use the home Bonferroni or you use the Bonferroni procedure correction. But all these things should be listed in your write-up. So in terms of graphing categorical variables, again, we kind of already went over this. My preference is to include kind of like a rain cloud plot where we have all the raw data, we have the density plots, but we also have our mean estimate and our confidence intervals around that estimate. So that's probably what I would recommend if we're going to graph these categorical variables. And these are just kind of different visualizations for the 5-level factor and then the 2-level factor. Again, it's up to you what you would prefer, but at least at the bare minimum, have the mean estimates and then the confidence intervals around that mean estimate at the bare minimum. And you could also throw in some box plots here too if you wanted to. But. So just to wrap up, so hopefully you can see how we can easily extend the linear model framework from a continuous predictor variable to a categorical predictor variable. I think it's a very, very easy extension, and it's not too difficult. Where I think the difficulty lies is in the interpretation of the intercept and the slope, depending on the coding scheme that you use. But once we have that down, I think it's fairly easy to use these different coding schemes in the context of a general linear model. But what I want to emphasize here is that our interpretation of the test statistics and statistical significance are all the same. So if we go from the continuous variable to a categorical predictor, pretty much all the same things. And so are the assumption checks. So we talked about assumption checks before break, where we have to test linearity, homogeneity of variance, and the normality of residuals. We can do that with our categorical predictor as well. This is just using performance check model, but we can check all these things. And these look kind of weird because these are fitted values and these are just the means for each group. But we can check to see if this reference line is horizontal. If it is, we can say that that particular assumption has been satisfied. We can also do the same thing for linearity, and we can also look at the normality of residuals as well. So all the things that we did with a continuous predictor, we can do with a categorical predictor. And we're going to continue to build on this. So that is all that I have. So next week, we're going to be talking about effect size and power analysis. So that should be fun. So that is all that I have. Does anyone have any questions? Fun stuff. So yeah, if you guys don't have any questions, you're free to go. Wednesday, we're going to have a lab. So we're going to kind of make all of this concrete by applying it to a specific example. So hopefully things will be a little clearer. But bring questions if you have them about coding schemes. I can answer them then. So Alex and Faustine, so I recorded lecture today because Ari's not here. Are you okay with me posting it to the website? Yeah, okay. Just want to get your approval before. See you tomorrow. Bye. See you on Wednesday, Alex. Were you able to get a new laptop? or not a new laptop, use your old one?
I'm gonna get my MacBook from California.
Awesome. Were you able to do the linear regression lab? Okay, and you did it all in pandas,
I
or?
did it in pandas and then did the bridge thing for the what is it, the normality test.
Okay,
I just
awesome,
set the data frame over.
awesome. Yeah.
I was
What's up?
wondering for lab 4, I honestly just like totally forgot about it, just like with the fall break.
Oh, that's
and
fine.
everything. Is it fine if I turn it in like with the?
Yeah, so
all
do,
of that?
yeah, so on Wednesday, if you're gonna be here for the lab, just do it at
Okay,
that time.
sounds good.
Yeah.
Cool. Thanks so much, Jason.
Uh-huh.
All right, see you Wednesday.
See you Wednesday.